Wow,
that ominous
the voice of Zoom.
Yeah. The antenna will probably just show up when he shows up, so maybe we can go ahead and get started then. Okay, so we're very happy to have Kevin here today with us, who will, I guess, tell us either how to probe the axion-electron coupling or how not to.
Yeah, thank you very much for the invitation. So, hi everyone, I'm Kevin. I'm a postdoc at Berkeley right now, and I'm going to talk today about some work I did a few years ago with these folks, Asher, Alex, and Tanner over at Fermilab. So let's just get right into it. So you've probably heard a lot recently about people looking for ultralight dark matter, and I think there's a lot of good reasons that we should be trying to look hard for it. Some that are well known and some that are a little less emphasized. Of course, the well-known part is that it seems to explain the apparent amount of dark matter, and there's a variety of simple production mechanisms that can naturally give you the right amount of dark matter. But in addition, it is generic in the sense that there are many UV completions which automatically give you weakly coupled ultralight fields in the infrared. And so that means that even if you're not really entirely sure what the UV physics is, there's many ways of getting to the same conclusion. But there's also a couple more that I think that deserve to be better appreciated. The first is that this is low-hanging fruit in the sense that for many families of ultralight dark matter and their interactions, the only way to search for it is by making a new small-scale experiment. But quite often, these experiments can be extremely effective relative to their cost. In addition, of course, it has the advantage of being minimal, in the sense that when you search for a new physics, there's often a risk of entering some kind of combinatorial explosion, where if you say, I have more than one field, I have 2 fields, 3 fields, and I say there's some interactions, it is very easy to get lost in this maze of dozens or hundreds of possibilities where it's not really clear what space you're actually excluding when you find something and don't see anything. Or what is the best to optimize chance of discovery when there are so many possibilities. And so in this case, for ultralight dark matter, there is actually a finite number of problems you can look for, which give a finite number of physical effects. So in some sense, we really can say, this is the parameter space that is important, and we can measurably think about what fraction of it we've covered. And that is also the final thing, which is that it's bounded in the sense that when you there is a controlled framework to allow you to know which interactions are important, which is good old effective field theory, the concept that is consistent with all experimental data ever taken in the world, which tells us that there are only a few interactions of ultralight dark matter that can exist that are natural and leading when the interaction comes from high energy scales. So I'll give you a case study. Let's suppose we were looking for the axion, which is motivated for various reasons. And so if you had an axion that arose in field theory, then here's a standard way that would happen. So what would happen is that you would begin at some very high energy scale with the spontaneous breaking of some chiral symmetry, usually called Pinchik-Winn symmetry. And this would give you some Goldstone boson called the axion with couplings to fermions that are of this form. Then you'd say, well, because it's Goldstone boson, we should probably recast the interactions that explicitly have derivatives of the axion field. And you can do this by applying various chiral field redefinitions to the fields, to the fermion fields, which also will give you couplings automatically to the cage bosons like this by anomalies. And then, of course, we can also integrate the coupling to FF dual by parts. And then finally, usually we're talking about what's happening at low energies. So these are couplings to quarks and gluons. We actually care about nucleons and electrons. So then take the low energy limit and we get this. And let me actually change the zoom thing so I'm not showing, there we go. So the point of all this story is that the details aren't that important. What is important is that, So the important part of the story is that in the end, you get a few couplings to fermions. And these are all the ones that you would expect to have at dimension 5 without breaking any additional symmetries that we know are pretty good. And so this is what you could have written from the beginning by just saying, well, if I postulate I have some axion field, and I just write down all the terms that could appear in dimension 5 effective field theory, you would get these 3 terms. And then if I have a generic story for how it arises in the ultraviolet, you also get all 3 terms. And so in that sense, we know what to expect at low energies if you're looking for an axion. So now what do? We go in the lab and search for these 3 terms. And so if you look across the world, there's actually a huge amount of experimental interest in searching for these terms. So the most famous one is the so-called axion-photon coupling, which I've written in this form. So this is WA coupled to the Chern-Simons current, electromagnetism. And this is the subject of a very robust experimental program. I've put this map together of all the active experiments right now that are looking for axion dark matter through this coupling specifically. It's all over the world. A couple of them actually just started up this year. And in addition, they're very widespread in the sense that if you combine the sensitivities of all these proposed experiments, they can probe the QCD axion across 10 orders of magnitude of mass. That is a huge chunk of where it could possibly be. And all of these experiments basically run the same principle, which is that when you have this coupling on, what will happen is that there will be an effective current, which is a source in Maxwell's equations, which depends on the value of the axion field, its time derivative, times the background magnetic field. So this is the central mechanism for all these experiments. This gives you a current, the current gives you some kind of fields, and you're trying to measure the fields. Now we can look, some people also look for the axion-nuclide coupling, so it has this form. And this is something that's less well explored in the sense that there are only a few proposals and only a few collaborations that have made some progress. But the basic idea behind probing this coupling is that what it will do is it will apply a spin torque to the spin of a nucleus, and that torque is going to be proportional to the spin of the nucleus across the spatial gradient of the axion field. And so then what people can do is that we have very good ways of controlling nuclear spins and measuring nuclear spin precession. In particular, if you have a very well-made nuclear magnetic resonance experiment, there's an effective quality factor of these oscillations, which is in excess of 10 to the 10. And that's because these nuclear spins are exceptionally well shielded from their surroundings. And so because you can get these enormous resonant enhancements, you can get very, very strong sensitivity to this term. So today I'm going to tell you about the axion-electron coupling. And so what I did was 2 years ago, I decided to compile everything that's ever been done to probe this coupling. And so I eventually made this exclusion plots. Yes.
So these last two couplings, are they special to the axion in any way, or is it just any scalar could have worked?
Yeah, so this is, so part of it is that it depends on what you call an axion. So some people would say it has to be the thing that solves the strong CP problem, and if you say that, then this can be just something else. So if you say I have a scalar field, and I also say that I want the scalar field to not break any symmetries to standard model that we know are really good, like baryon number or something like that. And in addition, not to additionally break CP, and also that should be a derivative coupling because otherwise its mass would get a huge correction. So those kinds of constraints, then this is one of those, these are basically the only things you can write down for the couplings of that scalar field. And so in that sense, you can say it comes from some generic scalar. Yeah. So in this talk, I'm going to be relatively agnostic as to where it comes from. Though there is a motivated band, which is that if it also solves a strong CP problem, then it should be in this region. So here's the situation right now, which is basically there is nobody actively searching for this coupling, and even relatively, I'd say, optimistic proposals to search for it often just barely go past the existing astrophysical bounds. So these are bounds that are irrespective of there being dark matter. This is from white dwarfs cooling faster than expected. This is from xenon entities seeing axions emitted from the core of the sun. And so it seems like this is a bit of a hole. And so there's a good reason for that, though. So in this talk, I'm going to explain what this coupling actually does to electrons, why it's hard to actually look for it, and also why some people thought it would be easy. So this is one of those problems is that if you begin looking in literature for claims that has probe this coupling, most of the papers you will see in the past year are wrong. You'll see some claims that you can probe it to 20 orders of magnitude stronger than astrophysics. All those claims are wrong. I'm going to show you why. And then finally, I'm going to show you that actually, despite all this, you can still use it to probe a QCD axion with good sensitivity. You have to work hard, but I think it's possible. And I'll show you a new experimental concept to do that later. So, yes.
On the previous slide,
Yes.
superradiant cooling of black holes is lower mass than this, or?
So that depends on the axion-photon coupling. So if you have that, then it would take place around these masses. So it would be on here, but because it's due to a different coupling, I haven't really included here because this is just the electron. But yeah, in principle, that could be strong constraints. So if you had if you assume you had a QCD axion or something, then these couplings have to be related to each other, and then you can say something about this one indirectly. But if you have some generic scalar or an axion-like particle where these couplings are independent, then you can't really say much from superradiance. Yeah. So now I'm going to show you. So let's jump into it. So what does this coupling do? Well, this is the term Lagrange. So it's G. The coupling has derivative of the axion field times E bar gamma nu gamma phi b, which is the axioelectric current of the electron. And so this always had bothered me because when I was a young student, I had got my introduction to this term in the following way. Once, I was in quantum field theory 2, and we were introducing anomalies. And they said, what does the anomaly do? They said, well, the anomaly means that this current isn't conserved. And I was like, okay, but what is this current physically? And they said, well, it's a thing that's not conserved because of the anomaly. What else is there to know about it? In order to actually intuitively see what this term does when the axion is a classical field, you need to think about its classical limit. And so there's a very simple interpretation of what it is. So if there was no gamma 5 here, you just had E bar gamma nu E. Everyone knows that is. That's just the vector current of the electron, which for a particle is just its 4 velocity. And similarly here, the quantity that this is for a single electron, if you take the expectation value in a single electron state, is the particle's spin 4 vector. So in the non-relativistic limit, the spin 4 vector is this quantity, which is basically the spin direction in the spatial components, and v dot the spin, so basically helicity, in the time component. That's what this quantity is actually measuring. So that makes it easy to see what the thing actually does when you take the non-relativistic limit for a single quantum particle. So when you have this reduction, you plug this in, and then you expand out the take the sum. Then this is the Hamiltonian you get. So you get a Hamiltonian that has a gradient, a spatial gradient of the axion field times the spin of the electron. And also, we get a term that looks like the time derivative of the axion times the spin dot velocity of the electron. So velocity here being p minus qa over m. And so these two terms have names. The first one is called the axion wind term. And so because it looks like the coupling to, say, an external magnetic field, it's pretty clear what it does. It will apply a torque to all the electron spins, and that torque depends on the spin direction across the gradient of the axion field. And then this other term is called the axioelectric term, and I'll discuss a lot more about what this term does in a second. So if you haven't seen much about axion searches before, I should remind you that these are all cases where when you have axion dark matter, the axion is it can be thought of as a classical field. So you should think about this A as just literally being some number at every point in space and time. It is roughly like oscillating sinusoidally. The frequency of this oscillation is set to be typically around gigahertz if you have a micro EV axion mass. And in addition, the spatial gradients of the field, they depend on the average velocity of dark matter, which typically is about 10 to the minus 3 in the galaxy. And that's set by like the size of the gravity well in the galaxy. And so that means that anytime you have a spatial gradients, you end up with a factor of 10 to the minus 3 suppression compared to if you had a time derivative. So this means that on the face of it, the axion wind spin torque is a suppressed effect because you automatically have to eat this 10 to the minus 3 penalty. Now, the axioelectric term does not have this suppression. So it seems at first glance, this term should be more important. However, there's a lot of ways to get to estimate the effect of this term incorrectly. So I'm going to show you some things that would seem natural but actually end up not working. So let's just get rid of the other stuff we don't care about right now. Let's have no B field. Let's get rid of the gradient for now. And so now that I have no B field, I can actually gauge fix. Let's get rid of the scalar potential and just set e to minus a dots. So this is all to clean up the terms we don't want at the moment. So this is the Hamiltonian you get, the normal one plus the axioelectric term. And so if you stare at this and think, what does this actually do? Well, one thing that you might imagine it does is it implies that there's a Hamiltonian density for the electromagnetic field, which is that there's a current, that whenever you have a current, it will show up the Hamiltonian density of the electromagnetic field as J effective dot vector potential. And we do have something dot into vector potential here. So we have A dot something. And so that suggests that whenever you have an electron just sitting still, they should give you some coupling that excites currents. And that effective current should be G A dot Q over M times the density of these, the spin density of these electrons. And just naively, because that's the coefficient of A. And that seems to be a pretty large current. But that's not actually what happens. And the reason is that this is not really the right way to physically write down this Hamiltonian. The best way of doing it will be just write everything as one big square. And so if I can combine the square and throw away an order G squared term, which is going to be completely negligible, then this is what I get. So I get a Hamiltonian of P minus QA minus G A dot sigma, where sigma is the spin orientation, squared over 2F. And so when you write it this way, it's manifest that what we're doing with this term is we're not actually changing how an electron sources electromagnetic fields. What we're doing is we're adding a new force to the electron, because this thing is just added on to the vector potential of the electron fields. And so it's like we had an extra contribution to the electron, the vector potential of G over Q times A dot times sigma. And so then that vector potential gives you an extra force, which is minus dA dt times Q. And so that means that the force on the electron is going to be minus G times the time derivative of its expectation value of A dot times sigma. A dot and where the particle is, and sigma just being the particle spin orientation. So that is what this thing actually does. It gives you this extra force. But unfortunately, this force is generically very, very small. And that's because if I had an electron sitting there with no spin, without some like really fast spin precession happening for some reason, then the force ends up being depending on the second time derivative of A. So that means, and every time derivative will suppress you by the axion mass, which is very, very small. So the more derivatives you have, the smaller these effects are. So this is quite discouraging, which is that it looked like it was a one derivative term, but actually the effect comes with two derivatives. However, then you could say, well, wait a second. If the force depends on the second time derivative, and I integrate force over time, then that will give me change of momentum, which is proportional to the first time derivative. So that means that if you just naively said, I'll just integrate this force over time in a material, then I'll get right back to having a first derivative. And this, again, is actually just the same as what we started with. So if you could say, well, all these particles are just accelerating this effective field, then they will accelerate up to a speed proportional to A dots. And this, again, is a really large current if you actually numerically evaluate it. Like if you actually plug in the numbers here for just an average magnets, this is 10 to the 3 times larger than what people are looking for in these axion-photon experiments. So if you could actually get a current this big, this would make it very easy to probe the QCD axion. But unfortunately, it's even more subtle than that. That still doesn't work. So I'll give you here's the next layer of the story. So how large of a current do we actually get if you have this effective field that's proportional to the second time derivative? So the simplest case is to say we have a dielectric, so some insulator, where all the electron spins are pointing the same way, which is not, I mean, it doesn't happen generically, but you can imagine cases where most of the conduction electrons are, most of the valence electrons are pointing the same way. So here's what happens. So first off, the current induced in this medium is going to be the rate of change of its polarization, because from Griffith's electromagnetism. And so that's going to be epsilon minus 1 times the rate of change of E, because of the definition of permittivity. So this is all, college E&M. So this looks like, so now at this stage, we have a current which is now suppressed by 3 time derivatives, so it's even worse. But we do have an enhancement because epsilon can in principle be a very big number. So let's continue thinking about this. So once you do this, at the same time, the material will create an electric field because you have a current in it. And this can cause shielding of the effective field from the axion. So the way we figure this out is we write down the wave equation inside the medium, which is curl E plus epsilon E double dot is minus JA dot. That's what it is when you combine Maxwell's equations. And now the axion, we're neglecting its gradient, so anything that involves spatial derivative is just 0, everything is uniform. So that means that when you solve this equation, what you get is that there is an extra E field in there, which is proportional to 1 over epsilon times J. And so that means that the total polarization current, which is due to both the effective field from the axion and the shielded E field induced by the medium, because when you're inducing current inside it, when you combine these things together, you get this result, which is that it's proportional to epsilon minus 1 over epsilon times E effective dot. So as I said before, this result is now suppressed by 3 time derivatives, so it's really, really small. And also, you no longer get enhancement if epsilon is big, because with the bigger epsilon is, it doesn't actually make this quantity any bigger. So this is very discouraging. Now you might say, well, this is, of course, it's because you're considering an insulator. An insulator has the electrons not free to move. So that means that, of course you couldn't get a big current in there, right? We should try something like a conductor, maybe even a superconductor. But unfortunately, that doesn't work either. So if you had an ideal conductor, that means that all these formulas still work, but you have to include a complex valued permittivity. So for an ideal conductor, it is 1 plus I sigma over omega, and this imaginary part can be enormous if the conductivity is huge. And for an ideal superconductor, so this is one of those things where the electrons are perfectly ballistic, there's no dissipation, then a toy model for this epsilon is 1 minus plasma frequency squared over omega squared, which again can be an enormous number because this is EV scale. So then you might think, well, this is how we would get it to work. Because some of these things, like conductor and superconductor, have 1 over omega enhancements or 1 over omega squared enhancements in the permittivity, which means that we can get some enormous current. And indeed we can for the first order current, which is proportional to epsilon minus 1. That is enhanced. But the whole thing, including the shielding effect of the medium, is proportional to epsilon minus 1 over epsilon. So if you make epsilon big, it doesn't actually give you any more current than you would have had just from a regular old insulator, which is very, very frustrating. And so that means that no matter what you do, you're never going to get parametrically more current than E effective dot, which is 3 time derivatives. So that's why you can never get the enhanced current I was talking about in the previous slide. And there's a physical explanation for this, which is basically, this is just how shielding always works. So if I have this is something that you might remember from sophomore physics classes, but if I had a charge and I suddenly accelerated it to the right, so this is the picture of its electric field at some time, then it'll make a shell of radiation propagating out from it. And inside that shell, the E field induced will be primarily pointing to the left. And that's what shielding is. Basically, whenever you accelerate something, you'll make a shell that wants neighboring electrons to accelerate the other way. And so the better you make the material, the more free you make the electrons to move, the better they are at shielding this field from the axion. And so no matter what, you never get enhanced over the really, really bad result for an insulator. So that's very discouraging. Still, you can think, well, we can still try to get some constraint from this. So because it's proportional to the 3rd time derivative, and each time derivative gives an axion mass, we should probably crank the axion mass as high as we possibly can. And so the highest mass that you could have for still be ultralight dark matter are things around the EV scale, which corresponds to extremely fast oscillations like those of optical light. And indeed, people have thought a bunch about how to absorb axions in media in this regime. And so this is an example of some calculations that have been done recently. The one in our paper was using this dielectric multilayer thing. But the point is that even with relatively optimistic assumptions on assuming that there are no backgrounds and things like that, it is very hard even to beat the existing astrophysical bounds. And that's just because this 3-time derivative thing just kills you. So because of this, we conclude it is very, very hard to prove this coupling because the real effect of the axioelectric term is a 3rd time derivative. And the axion wind term has a 10⁻³ dm velocity suppression. So it seems hopeless. But then if you look at the literature, you will find many papers saying that not only is it hopeless, it's actually really easy. And so here's a list of 8 papers recently that are published in good journals. And they say, here's a sampling of constraints that are claimed in these papers on the coupling. So notice that the y-axis scale is very different, and so is the x-axis scale. And so the source of these claims is that all these papers basically say there is some kind of effect of the axion field proportional to A, not 3 time derivatives, not 2, not 1, just 0 time derivatives. And that seems impossible because the Lagrangian started with a derivative on it. So how could we have gotten rid of the derivative? So how in the world could people convince themselves that this is possible? And why do these experiments not actually have such great sensitivity? That's the thing I'll tell you about next. I'll pause a second if there are any questions.
Sorry, is there, are these papers, are they also using the axioelectric effect? Is that the claim?
Yes, it's related to that. I'll show in the next slide.
Okay.
Yes. It is related, it's like a twisted kind of interpretation of it. Yeah. Okay, so what is going on in these papers? Like, why is there even a confusion at all? Because the way I said it before, it doesn't seem to leave much room for confusion. So here's the problem. So the problem is that you can write the axion-electron coupling in 2 equivalent ways. So I think this is something I mentioned in the very first slide of this talk. So if you start with the derivative coupling, which is the one we want because it makes it manifest that the effects depend on the axion derivative, you can apply a chiral field redefinition to put it back into this form. And this form has just the axion field, no derivatives on it, times E bar I gamma 5 E. And so this is something that's been known for a very, very long time. But in the end, they will give you, equivalent physics because it's just the field redefinition. However, if you then say, well, let's take the non-relativistic limit for a single particle and compute the Hamiltonian, they look very different. So the Hamiltonian, as I mentioned earlier, in this way you get the axioelectric term. I'm going to continue dropping the spatial gradient because it won't matter for this conversation, it's all the same. But if you take the non-relativistic limit of this one, which is actually, it's a bit grungy. You need to do these either this higher order Pauli reduction or a fully width transformation or other things like that. But once you do it, this is what you find. You find a different axioelectric term, and also this term with no derivatives on A. It's kind of puzzling. And also, if you never knew about Lagrangians and you were just doing quantum mechanics, you could also go between these. And so if you said I have a Hamiltonian like this, what I can always do in quantum mechanics is I can do what's called a unitary state redefinition, which is to say that I have some states in my theory, I just multiply everything by unitary matrix, the same unitary matrix. And that is like the quantum analog of, like, say, changing your reference frame in classical mechanics. That is something you can always do. Of course, you have to replace all the observables like U dagger O, U. And then this will, of course, keep all the observables the same. And in this particular case, here's the explicit U that gets you between them. And so this fact that the interactions can be written in these 2 very different looking ways has been known for a very, very long time. So back in the 1950s, there was a whole bunch of arguments about pi and nucleon interactions. Feynman has a funny story about this, of how some people were arguing, and then he invented the Feynman diagram and showed how they were how one of them was right. And it's something that we've known for a long time. But when you're going to the level of laboratory experiments involving things like bound electrons and dipole moments and things like that, it is not completely obvious how this works. Because we know from very general principles that this side should give you the same physics as that side, but it sure doesn't look like it gives the same physics, because first off, there's a factor of 2 that's different over here, and second off, there's a term with no derivative, so how could that possibly be the same thing? So I'm going to show you how it's the same thing now. So first thing is, let's focus on this term, the axioelectric term. So it's very weird that the coefficient of the term is different, depending on how you set up the calculation. So for simplicity, let's just take the charge to 0, so this is the only thing that shows up. And this is very weird, because I just told you that this gives you a force, and the force gives you a current. So how can the coefficient of force possibly be just freely adjusted by doing something that doesn't change the physics? So the resolution of this is that, well, you can actually always do that. And so that's a shortcoming of only considering the Hamiltonian for a single particle. If you have a Hamiltonian with a single particle and then something that gives force in it, you can always remove that force. There's always a transformation that does that, because that corresponds to simply working in the reference frame that's moving with the particle. And so this is something that you can do with classical mechanics as well. And so that means that if I want to see if a force is a real force, like can it actually be measured in experiments, I have to calculate the relative acceleration of more than one particle. Like that's the only way we can actually ever measure if something moved or accelerated. And so that's what happens. So if you did the same derivation But from the beginning, we had either two fields or one electron field with two electrons in it, a state with two electrons in it. Then you did the same calculation. Here's what you get. This is on appendix like E of my paper. So for the derivative interaction, you get something what you expect. There's a potential between them, maybe Coulomb or something like that. And then you get, of course, the axioelectric term for each one. But then if you did it the other way around, you get something else. You get the same thing, half the axioelectric term, and then this weird, annoying extra term that depends on their mismatch of spin directions. And so that's what always happens, which is that if you try to get rid of this axioelectric coefficient by make it smaller, like half as much here, you can even get rid of it completely. What you always do is you make these other annoying terms that encode the exact same effect. So an example of this is if I had two electrons in a molecule, then the axioelectric term, and they have different spin directions, this would excite the molecule, they wiggle in different directions, and then if you try to get rid of the term, but you put this one in, this would also excite the molecule, and everything would stay the same, it's just that it's now much harder to compute what happens. And so that's why this original coefficient is actually the correct, physically correct one. Whenever you try to adjust the coefficient, you induce other terms that do the same thing, but in an unintuitive way. So next up, let's talk about the dipole moments, the electric dipole moment. So now I'm going to simplify again by taking dA dt equals 0. So the only term that shows up is this sigma dot E term. And so this is even more confusing. So in the second way of calculating it, you get a term that looks like a bunch of constants times A times sigma dot E. And that's kind of weird because we learned in, you probably learned in Griffith's electromagnetism textbook that this is what a dipole moment is, right? So when you have a magnetic dipole moment, it means you have a term in the Hamiltonian that looks like sigma dot B. And when you have an electric dipole moment, what that means is you have a term proportional to sigma dot E, right? That's literally what it is. Now that's not quite right because when people look for the particles with electric dipole moments, they really look for this term, which is relativistic. So this is the term in the Hamiltonian of the particle that actually gives you a relativistic EDM. But then when you take the non-relativistic limit, you get, of course, d sigma dot E plus relativistic corrections. So still, it looks like, at least in the non-relativistic limit, this is what a electric dipole moment is. But in fact, and this is something that is, again, it's been known in the 1950s, but is actually quite tricky. If you have a charged, non-relativistic particle, a constant EDM doesn't actually do anything. An EDM of this form. So the physical interpretation of this is, well, and let's suppose I just had a charge, and I said also it has a dipole moment. And so of course we know a dipole moment is equivalent to superposing opposite charges separated by some amount. So let's say it's plus Q minus Q separated by L. And then the charge configuration that results in is just the same as what we started with, but where the charges has been shifted a little bit. And so the problem is that in the non-relative limit, in a constant EDM looks exactly the same as if we just didn't define the position of the particle correctly. If we had worked in some weird thing where the position operator was defined, so we said it was here, while the charge was actually over here, then it would give you this term, the Hamiltonian. But that's not actually a dipole moment, that is just an artifact of defining position wrong. And that's actually the key idea behind what is called Schiff's theorem, where they shield EDMs. People say that Schiff proved that EDMs are screened, but what he really mean was basically if you gave the nucleus an EDM, it's as if its charge is shifted over, and the electron cloud just follows where the charge is. So that's why there's no EDM of that neutral atom. So, but now this might be even more surprising to you because I just told you you can't actually measure an EDM, but then when experiments measure, what are they actually measuring, right? And so they measure something more subtle. So when you actually look for a true EDM for a charged particle, all the physics is actually in the relativistic corrections. So one thing that happens for example, that's in this term, but not in this non-relativistic limit term, is that when it's moving with some velocity, an EDM will pick up a magnetic dipole moment proportional to the velocity. In addition, a real EDM, if it's moving along its length, will length contract by amount proportional to v squared with c squared, while this fake constant shift position does not length contract. These are the kinds of things that are actually searched for in EDM experiments. Like if you calculate, these are actually the operators that actually matter. And this is shown in this really nice pedagogical work by some experimentalists, and I think Dan Jackson about 15 years ago. So unfortunately, what this means is that the term that we do get actually contains only the part of the EDM term that does not have a physical effect. So that's why it's actually a fake. You can't just say that this was probed by an EDM experiment. They don't probe this at all. Now, of course, if I let A vary over time, it does have an effect because then you get an axioelectric force. But that force is competing against the binding forces inside the molecule, or the atom, which are extremely strong. And so this also was estimated 10 years ago by some people that are really good atomic physicists. And they found that parametrically, the effect is suppressed relative to what you would imagine naively here by a factor of MA over binding energy squared. And that is an extremely, extremely large suppression. So that means that it's basically hopeless to use this to search for the axion. So that's why this term, it looks like it's doing something, but it actually is just a trap. And so now we've come all the way full circle. So now we must actually, unfortunately, because I now show that everything associated with this axioelectric term is not very useful, we actually have to search the axion wind spin torque. There's no way around it. So now what does this axion wind spin torque do? So I mentioned a while ago, what it does is it tilts the spin of an electron by an amount proportional to the gradient of the axion field. Now, what that will do is that when I tilt the spin of the electron, well, the electrons also have magnetic dipole moments, so that'll yield a transverse magnetic field. And also it'll oscillate over time if the spin is precessing, and so on. And so if I asked you a priori, is this easier to do for the axion-electron coupling or the axion-nuclide coupling? It would seem a lot easier for the axion-electron coupling because the magnetic dipole moments of of electrons are much higher. They're enhanced by the fact that the electron is much lighter than the proton, which gives you a 10 to the 3 bonus. So it seems like this is the easy way to probe the axion, but that's not true either, because the problem is that, as I said earlier, for the axion-nuclide couplings, you benefit from these huge quality factors in NMR experiments, and for electrons, you never get high quality factors because they're charged and they're strongly interacting with each other. So in this space, there's two things that people do. So the first thing is, let's just have a solid magnet where I have a lot of electrons with aligned spins, and so automatically, the excitations in these magnets, which are magnons and so on, are automatically around the milli-eV range. But there also are strong interactions between the electrons, which mean that you cannot get these enormous quality factors. And I'll explain. But you can still press on, and then what will happen is that the signal will be that you will tilt the spins, which gives you an oscillating current, and it'll cause some radiation to be emitted from magnets. And I'll talk a lot more about this later. The radiation is around the milli-eV energy, which corresponds to terahertz frequency. The other thing is that there's some tricks people can do, which is that you can either have what I call separated or locked electrons. So there are ways of making it so the electrons can rotate with a much higher quality factor than if they were just in ordinary magnets. And this gives you much higher quality factors and also typically much lower resonant frequencies. In this case, when you have a lower frequency, you don't want to detect radiation. If we don't know how to detect very low frequency radiation, what you measure is the near field B field, which is quad static, and you just put a magnetometer next to the sample, like a squid or something. So this first looks pretty good. So I'll give you some examples of how people did this. These are all, of course, proposals. No one actually has done this yet. This is just theory projections. So there's a family of experiments that I call separated electrons. So we can search for this electron spin precession in the near field by using electron storage rings. So these are just like lumps of groups of electrons traveling around a storage ring. Co-magnetometers, which just means some magnetometer, which is where the spin is compared against the spin of something else, and also nitrogen vacancy centers. And so this is a proposal from a few years ago where you can have diamonds have these defects in it, and each defect will carry an electron whose spin can precess. And then you can have these separate from each other. Now, in all these cases, the separation between the electrons is much larger than the atomic distance scale, and that's why you can have pretty good resonant enhancements. But the problem is that at the same time, this dramatically lowers the number of electrons that contribute to the signal. And so once you cash in that penalty factor, even with the relatively optimistic numbers that you can take sometimes, it is still very hard to go beyond the physical value. You can improve by a little bit, but not that much. Now, on the other hand, you can also have what I call locked electrons. And so here's the idea here, which is that in some ferromagnetic materials, the spin is not independent of the orientation of the crystal. It has to be aligned along one of the crystal axes. And so in those kinds of things, the spin direction is locked to the crystal direction. So if I apply a torque to the spins, the entire sample will actually rotate mechanically. And so that's what happens when people try to make torsion pendulums that are sensitive to this. It will create an actual torque and an actual piece of material, and then that thing can be resonantly amplified and read out very carefully mechanically. But the problem with this way of doing it is that we don't get the benefit I mentioned earlier of the electron having a large magnetic dipole moments. In fact, we get suppressed because typically the nuclei are very, very heavy. And this little spin torque actually has to apply torque to rotate the entire thing, including all the nuclear mass. And so that ends up giving you, this means that you don't get any benefit over having a coupling to nuclei, for example. And in the end, it's very hard to beat astrophysics. I should also mention that every single curve I'm showing here is always going to be the most optimistic one that anyone wrote down anywhere. So how hard this is to actually make varies a lot depending on the experiment. So that's the state of the art for separated or locked electrons. So now let's go back to the solid magnets. So the solid magnet has been pursued by a variety of collaborations. So there are some strong projections here, which can even go in QC axion bands. And also there have been actually some experimental results. So this is actually, I believe, 3 or 4 separate papers. People actually tried to build these things. And basically everything that was in this regime used the same concept. So all of these things use what I call the ferromagnetic haloscope concept. So I'm going to explain to you what is this concept that everyone is using. So here's the idea. So I take a microwave cavity, and inside I put a small magnet. And so the spin in that electron spin in that magnet will have some resonant frequency. And then I tune the external field acting on that magnet so that that frequency is on resonance with the frequency of the axion field. And so that means that the axion will tilt the spin more and more, just like nuclear magnetic resonance, but with electrons. This is sometimes called ferromagnetic resonance. And then in the long run, there'll be some power being emitted from this thing in radiation. So that power scales like this. It scales as the effective magnetic field squared due to the axion. This is the thing that gives you the torque, times the volume of this sample, times the quality factor of the magnetic oscillation, times omega m, which I'll explain in a second. And people always use every single experiment uses the same material. They always use yttrium iron garnet. And if you're an applied physicist, it's a very famous material because it has the highest known Q sub m of any magnetic material by a lot. So here are the numbers. So the effective field of the axion is something depending on its gradients. The magnetic quality factor of yttrium iron garnet is 10 to the 4, and this is something that people work very, very hard to achieve. This is something that you have these microscopic spheres and you polish them extremely well, and they have to be spheres, and they have to put them, you have to attach these very delicately, and then you're able to achieve a magnetic quality factor 10 to the 4, which is still impressive given how strongly the electrons are interacting with each other. And this omega m is just basically a measure of how magnetized the sample is, but I've converted to units of frequency, so it's easier to convert. So numerically, this is about 0.03 MeV. So if you plug in some big numbers here, it seems like this can be quite sensitive. Oh, and then the last thing is that once this thing emits radiation, it's also tuned to be in resonance with the mode of this cavity. So then that radiation all gets excited in this cavity mode, and then you have an antenna that reads out that cavity mode, and then the power comes out. But basically, the power that comes out is just determined by this expression. So the problem is that it's very hard to scale these experiments up into something that would give you actually good reach. So in 2018, some people in Italy did it with one yttrium iron garnet sphere, which these things I think cost like $10,000, and they're almost too small to see. And it has that sample had 0.005 cubic centimeters. There's an upgrade done in Australia, which used a bigger sphere. And then the Italians came back the next year and they said, we're going to use 10 of these spheres, and they're going to be each slightly bigger than the last one. And so now they're all the way up to 0.1 cubic centimeters, but their sensitivity benchmark in order to hit the QC axion required 100 cubic centimeters. And the problem is that this crystal, even though it's a very well-known material, it does have the highest magnetic quality factor. It can only be made extremely slowly because the crystal structure is very complicated, only in these spheres of millimeter size. And it is hard to get a quote of this, but it seems that before the trade war, it would have cost $10 million per kilogram. And this is like kind of just like projecting up. Like this is, I don't believe there actually is enough capacity in the entire world to make a kilogram of this stuff. So it probably is in practice even higher. So this is something that is just difficult to scale. In addition, there's problems with like if you actually try to fill a cavity with this much of it, it wouldn't really function as a cavity anymore.
So how heavy is the 0.21 centimeter cube?
This thing, well, let's see. So this is a kilogram. So this thing is 1,000 less. This they had a gram in the last one, and that's 10 of these, so 0.1 grams. So I mean,
Not expensive.
yeah, I mean, this number has an error bar of like 2 orders of magnitude because it is very hard to. This is another thing, which is that when I think about new experiments, the manufacturers are very tight-lipped about how much things actually cost. Like there's no price tag on any of these things. You have to call them for a quote, and so and sometimes even for like this characteristic of the material, you have to call them for a quote. And I've been tempted to just pose an experimentalist and say, oh, I'm setting up a lab here, and I want, but I think this is the best estimate I could do based on some numbers someone put in a slide somewhere. Probably a bit higher though. But this seems a bit inefficient if you want to scale all the way up. And so here's another idea, which is that everything has been coming all in on how can we make the resonant enhancement as much as possible. But there are other concepts for detection that don't require strong resonant enhancement, where you try to go more broadband. And you gave up on the maximizing the quality factor, you can open up the kind of materials you can use by a lot. So for example, there's these materials called polycrystalline spinel ferrites. And these are very cheap and well mass-produced. Don't worry about all the names. Ferrite just means it has iron in it and it's not conducting. Spinel just means it's crystal structure, but it's basically the simplest one you can have in this case. Polycrystalline just means that it's made in a big vat. Instead of someone making a perfect single crystal, it is just made like 1,000 pounds at a time. And it's not literally to the point where you can buy this off Amazon, but it's like one step above doing that. So the benefit of this is that these actually have more magnetization than gig does because the simpler crystal structure, it's more electron spins per volume. And the quality factor is only about 100. So that seems pretty bad, but at least it's something.
That's why it's only a 4-star rating.
Well, yeah, I think Shakespeare would probably get a 5-star, but yeah. So I want to explain to you now an alternative concept that will use these kinds of cheaper magnets at much bigger scale. And so the problem is that if you did the same thing where you put a tiny sample in a microwave cavity, which to remind you, like the typical wavelengths of axions in this mass range are like millimeters to centimeters, so the cavity needs to be tiny. Like it just doesn't work. You need something that can be large. And so here's an idea. So the idea is that we just get a really, really big slab of this material. So let's say it's like a meter squared in area, and it's relatively thin. And so here's what happens when you have a slab. So there's going to be some current induced inside the slab, which is basically, this is again back to Griffiths, it's curl of 1 minus mu inverse times B effective. 1 minus mu inverse because they made a mistake 200 years ago. And so what this means is that there's going to be surface currents on the top and bottom surface of the slab. So let's suppose I had the magnetization pointing this way. The effective field tilts the magnetization, and that means that only surface currents in opposite directions are on the top and bottom. So at the same time, of course, the whole thing is precessing because it's in some external B field pointing along this direction. So it's not really a linear current, it's actually a circular current. There's a circular polarization being emitted from the ends, but I couldn't draw that really well. So then we want to know, how does this magnet respond? And then you might have realized, and this is something that I realized actually to my devastation when I was 23 years old. I had just finished my second master's degree, and I learned a lot of quantum field theory. I learned like many field theory classes. I even took some string theory, and then one day someone just asked me, like, so can you tell me how a magnet works? And I realized I didn't have the slightest clue how a magnet works. Like, not even this, I couldn't even begin to write anything down. Of course, I could write down mu, right? But what's mu for a magnet? I don't know, right? And so, that's because we typically aren't educated in this as particle physicists, but all of the electron engineers knew this in the 1950s. And so what you can do is there's standard equations of motion for the spins in these magnets, which are phenomenological, but they work pretty well. So there's, they precess, and there's a damping term. And also, you have to take into account that the permeability is a tensor. And so it treats for example, it treats the clockwise, counterclockwise polarization differently. But once you solve all that stuff out, then here's what happens. So I'm going to take the 1 minus mu inverse for the clockwise polarization only, because that's the one that gets enhanced. That's the way that this thing wants to rotate. And when you solve the equations, this is what you get. So this thing that determines how much current you get is the magnetization, of course, in the numerator, divided by this thing over here. And this is a typical resonant response. So basically, when the axion mass matches some characteristic frequency, then the denominator becomes small. It just becomes purely imaginary. So this is typically just what you would expect from a resonant response. Now, at the same time, this current will be driving electromagnetic fields outside the cavity. There will be plane waves coming out at either end of the cavity, on either end of the slab, which suck out most of this power. And so the amount of power deposited in the slab is maximized when you have resonance, which means that the axion mass matches 2 mu b times p naught. And this frequency is tunable because you can adjust how much external magnetic field it's in. So if you want to go all the way up to 10 Tesla, you can get probe axion masses of 10 to the minus 3 eV. And you go lower, you can probe lower masses. And then finally, I want to benefit even more from the scale. And so what you can do is you can place more layers. So if I had another layer of this stuff right here, and I tune the separation just right, then the amount of radiation emitted from this one would just interfere constructively with the one from the first layer. And so that's the kind of trick I can play. This is the kind of thing that doesn't really benefit. So this is where I'm winning by the scale, because the amount of power is coming out is growing with the slab area and also with the number of slabs. And so this is a lot like the Mad Max experiment, if you've heard about that. They probe the axion-photon coupling with a similar idea. They have a lot of layers with tunable separations. And that in the end, a lot of radiation comes out of the last layer, and they focus it onto a detector, and that's how they read out the signal power. It's a radiation experiment. So, so here I'm going to consider only the simplest setup for this, because there's actually a whole science. There's like multiple 100-page papers they put out about the way to optimize the thickness of the layers and the spacing. And it's even more complicated here because the permeability depends on frequency. So it's just very complicated to optimize. So I'm going to do the most naive possible thing. I'm going to space all the slabs by pi over ma, and I'm going to make each slab pi over n ma. And so the point of that is that this is going to be what's called the transparent mode setup, where basically what is emitted from one slab just constructively interferes with all the other ones, and nothing else interesting happens. This doesn't give you the best frequency, sensitivity range, but this is something that is simple to calculate. And so the power that is coming out of the end of this thing goes like this. There's first off a slab form factor. The form factor just is how much is the field being enhanced just from resonance of that one slab by itself. It goes roughly like 1 minus mu inverse, but the more general expression, which I actually use, has a bunch of effects because there's losses in the material as well. Then there's the number of layers, which I'm going to cap at 80 because that's what MadMax wants to realize. There's also another factor, which is that you want to make sure that the last layer is not absorbing that much of what came out of the first layer. That means that the index of refraction has to be mostly real, so that's another constraint. And then we'll take a meter square for the area as a benchmark. So what does this kind of experiment look like? So if you numerically optimize what to do in this experiment, here's what it looks like. So it looks different based on whether you're probing low masses, which I'm going to say are around 10 minus 6 eV, or high masses. So let's consider the low mass regime first. So in the low mass regime, the axion wavelength is quite long. It's like orders several centimeters up to meters. And so what I have is the slabs are very, very thick. And there's also not that many of them because I've made sure that you can't have this experiment being too big or else that would be unrealistic. And so you need a magnetic field that is very, very large. But the field it has to make is actually very weak, something like 0.01 Teslas. And in addition, the form factor within the enhancement for each one is quite large because there's a lot of random enhancement from each slab. Now in the high mass regime, you're talking about something completely different. So in this case, you actually end up, it's best to have a lot of thin slabs. But then it turns out that that only works if you're really far away from resonance, because then otherwise you would absorb too much of the signal from the previous slabs. And so that means that in this case, the form factor is actually sometimes it's not even greater than 1. You're well away from resonance. Now the quality factor is still affecting how many slabs you can have. So here, this is detuned enough that you can have 80 layers. And you also need a high field. So at the edge of here, we need 10 Tesla, here we need 1 Tesla. But the amount of volume you need that field in is very, very short because here, this is something where the length is only about a centimeter for the whole thing. So now I'm going to show you some benchmarks of how well this kind of thing could actually do. So here's the simplest benchmark. So this is, if I took everything off the shelf, so just the normal magnet, this is with the naive way of spacing it. And I had a standard Hempt amplifier. These are things that you can buy from a lot of commercial suppliers. And also you cool them to helium cryostat, which there are like many of these things. Then you can calculate the signal to noise ratio, and this is the kind of reach you would get. So you can already probe well beyond the astrophysical bound using the off-the-shelf stuff and the very cheap magnet that's almost on Amazon. Now you could try to get a better amplifier. And so the benchmark here is that a lot of people are thinking about quantum limited amplification in this regime, which just means that noise temperature is the minimum allowed by quantum mechanics, assuming you're reading a single quadrature. And in addition, for that to actually help, you have to put the whole thing in a dilution fridge. So in this regime, it's a pretty big dilution fridge. Here, it's like comparable to the biggest ones we have. Here, it's not that big. And so this is more challenging, but it has been done, like all this stuff has been done together in a variety of Axion experiments. And you do that, you can get well beyond the astrophysical bound. Still not looking very good for probing the QCD axion.
Quantum limited, that doesn't actually improve that much compared
No.
with the naive one.
No, yeah, because so when you go up here, like the fact that the noise temperature is equal to the mass of the axion, it just gets worse and worse, and yeah, so that's why quantum
Even
mechanics
in
are
the
good.
best place, it's just an order of magnitude.
Yeah, but that's just because these normal amplifiers are actually pretty good. I think they're not so bad. Yeah, it is an order of magnitude, but remember that's 2 orders of magnitude in noise temperature because it's squared. So actually, and if you're ADMX, you care a lot about every last factor. So, but this is not what I want to do if I want to probe QC axion up here. The reach is weak up here because the whole thing is very small. So that's why we're not getting as much volume enhancement. So now here's another benchmark, which is that when you're getting up to the masses of up to milli eV, the standard quantum limit is actually very, very strong suppressing your sensitivity. And what's better to look at is not actually the fields that are coming out, but the amount of energy that's coming out, because that's not subject to quantum limitations. So if you had something in this quantum ground state and you measured how much power is coming out, the answer is exactly 0. There is no quantum contribution to this. So if you put a bolometer, which is completely insensitive frequency, so it's not getting any of this enhancement about it being a narrow frequency or anything like that, then you can get a quite big enhancement over a standard quantum limit. Here I'm assuming these things are characterized by something called the noise equivalent power, which is just a measure of how noisy it is. I'm assuming here the target benchmark for the bread experiments. So I'm not completely sure how difficult that is to make, but I've just recasted the target and this is what you would get. But even that, you can do even better than that if you could have a single photon counter here. So the thing about bolometers is that they don't give you timing information at all. They just basically calculate seeing the mean energy coming in. And that's kind of rough information. Now, if you actually looked for single photons, then what you're limited here is by the dark time rate of your single photon detector. So you say, I just click every time a photon comes in, and then I need to make sure I can see that click above the background rate of clicks. And so here's a benchmark for photon counting. So here I'm assuming that we have thermal limited photon counting, which is to say that all the photons I'm seeing are due to the temperature of the apparatus. So of course, the apparatus is a finite temperature, everything's emitting blackbody radiation. You calculate how often that comes into your detector, and if that was the limiting factor, then this is the kind of reach you can get. Now, this is challenging because it is also known that, in this regime, you'll have all kinds of weird effects from dark counts that don't seem to have any particular reason. But then again, people have not tried cooling these things all the way down to dilution fridge temperatures at large scale. So I'm not sure how much of that would still be there if they cooled more. But anyway, this is the theoretical limit you could get. There's a kink in this curve because above here, we're limited by signal. So the background is negligible. You just need to have any photons at all. And then over here, you're limited by background because you need to see it above a high number of background counts. And so if you could do this, you could actually slice basically the whole DFSE axion for this order of magnitude. I will say that this is, for all the experiments projections we were comparing against, they all assumed this from the beginning. Like everyone else is assuming this with no noise at all. But this is the kind of thing you can do with this system. So there's of course a lot of open questions about how to do this, which is I've only done the simplest possible calculation here, and it's been conservative in a number of ways. First is we did this transparent mode setup, which is basically the simplest thing you could possibly do for multilayer. And the second is that when you have high MA, this experiment is short but really wide. And so it's like a few centimeters long, but it's a square meter area, which is very inconvenient for fitting into a fridge or inside a magnet bore. But you can imagine there could be more convenient geometry, like maybe you could actually curve everything. It's not obvious to me how best to do it, because if you curved it, maybe it'd be harder to tune it and so on, but this is the kind of thing that needs more thinking. The other thing is that I just took the benchmarks that are on the manufacturer data sheets for this, basically one of the cheapest things they sell. And it is possible that there are better magnetic materials out there that are still scalable to large volumes. In particular, this thing that we did, I believe is lithium ferrite. It has a high permittivity, which actually suppresses the volume you can have, and it has a relatively low quality factor. You can imagine something that there's something that's better than this, but still not as good as YIG, but you can still buy a lot of. And the other thing is that this is something that looks for all kinds of anomalous spin torques on electrons. And so you could ask, what kinds of other beyond standard model physics can such a setup test? And I think that it actually can be very good for probing things such as, say, dilatons or called Ramon fields, which is a topic for another day. So in conclusion, I've shown you that here that the axioelectric coupling is something that is minimal, very generic, happens in all kinds of models. The effects it actually creates are actually extremely simple, but it can be a little subtle to compute them, which has led to a lot of computing literature. And on the experimental end, every attempt to probe it has all used a single concept, but there are new ideas out there, this one and probably many more no one's thought of yet, which may allow scaling a stronger sensitivity. So thank you very much for your time.
Do people do photon counting with the YIG?
Yeah, so what is done here, let me just back up to the actual reach. So what has been done here is these projections assume photon counting. And then what has been done in the prototypes is there have been 4 experiments. I believe that 3 of them use, well, I think like, what was it? I think 2 of them used a HEMT, 1 of them used a standard quantum limit amplifier, and then 1 of them did this single magnon counting thing, which is there's some quantum tricks. So they kind of are doing single photon counting. It's a bit different because it's inside a cavity. This was the experiment done in Japan. And that is pretty good. But I think it is also got a good amount of dark counts. So basically, like the most cutting edge thing kind of is doing it. Yeah.
So there are some good reasons that axion will be first detected. Electron coupling.
So it's a bit, it's a bit tricky to say because admittedly, it is hard to make these photon counters. Now, I don't know, there aren't that many people that have tried very hard in this regime because this is what's called a terahertz gap for astronomy. So basically, like if you can't make telescopes that are sensitive here because that's the part that gets absorbed in the atmosphere, so you have to put it in space.
But let's say for DFSD axion, is it easier to see them in a photon? Just probe
like if you also had a Max multilayer. So
yeah.
I think that it's different. So what they have is they're assuming, I think, a benchmark that's more like SQL. But there is a difference, which is that in their assumptions, they're assuming a much better control of the slabs. And so there's something they call, for example, the boost factor, which I think they need to be about 100,000 in order to be reaching DFSC. But here, the equivalent thing, the boost factor here is what I call n times f. And there it's never bigger than 100 or so. And so in some sense, this requires less control of what the material is. And the material is also, I think, cheaper, but it is harder to make the final detector. So I would not say either way, like which one is easier. Yeah, but it is true. I mean, a very nice thing about it is that DFSC is the easiest thing to probe with this coupling, which is it just flipped from what you would usually see.
If there are no more questions, let's thank Kevin. Yeah.